Chris, and thanks everyone for sticking around. I realize it's been a long day and we're all ready to go to the reception, so I'll try to make it quick. And there's a laser here somewhere.
Use your mouse?
Yeah, I just use my mouse. So I want to talk about domain-specific languages. I've done a lot of work in PDEs, and I worked on the Phoenix project before, where we had a weak form language, and you could generate high-performance computing simulations from them. Why I'm in this session is because I've been working with Chris Keys a little bit and Kyle Manley on some geoscience kind of ideas. And I think that a lot of people in the geosciences and engineering in general kind of just take a lot of black box software. And my view is to let's get underneath it so that we can actually compose the tools that you're using. I mean, at the end of the day, geoscience is solving a lot of PDEs. It'd be nice to switch out some of the methods that you're using to actually solve them in different ways, or add your own sort of physics and things like that. And Ignition is my own project that put together a growing number of little languages that kind of do explore different aspects of technical computing or scientific computing. So I have a lot of collaborators, a lot of from the Phoenix all over the world, and then Kyle with one called Mini-Claw that Ignition can kind of generate through. So the Phoenix, a lot of this work grew out of the Phoenix program, but it's kind of like, let's look at other things besides just weak forms of PDEs. And that's where you can, Rayon was a rheology thing I built on top of Phoenix, and Ignition is the kind of what I'm talking about today. So the first kind of to outline, I'm just going to give a kind of an idea of why we do code generation, how you do code generation. I'll talk about Ignition a little bit and how it kind of, different topics around it, and then a very brief conclusion. So code generation. So why do we do code generation? And it almost seems today like people are talking about code generation a lot, especially at coding conferences or scientific computing conferences. But when I started this kind of thing, code generation was a crazy idea. Why would you ever do code generation? Just write your PDE framework in C or C++ and it'll be done. But the big kind of thing is that a lot of these codes, if you ever try to do things that are actually need to be the speed of the computer, reworking the architecture or optimizing something that makes the code slower, where when you have a code generator, you can kind of just have a script that switches out these guys, and you can generate the codes often in sequence or in some iterative method. Often, especially in performance, I find that you might be trying to fix one performance bug, but find another performance bug pop up somewhere else. So having that ability to switch these things out and run on different types of computers was very interesting. And as I say, your mileage may vary a lot. So don't think of code generation as a silver bullet, but as one tool in the collection of tools. So the way I've kind of always looked at it is start with a domain-specific language, because domain-specific languages, while you may be able to go with general performance and get 5, 10x, oftentimes if you pose a problem in the right domain, you can get many orders of magnitude more speed. And we showed that with the Phoenix, where we were actually able to get finite element calculations up to 1,000 times faster by just taking the right domain optimizations. And so domain optimization is the idea of an expert knows this domain, and then we generate for any number of models and things like that. So just to give kind of a history of some code generation projects, I call the early, the ambitious, and the unifiers. The early kind of included Atlas and FFTW, people who basically just generated based upon block sizes, sometimes called auto-tuning. The ambitious, there started to pop up quite a few subdomains that started using these ideas. Spiral is one that's now used on every Intel chip. Tensor contraction engine is another for chemistry that really took down chemistry code from taking months to build to hours, and ran just as fast in Phoenix, which I kind of mentioned already. And now the idea is like we want to unify these things. We want to be able to intersparse them, use them for different compilers, and get to the machine. So Ignition is one idea to run this. So we want to find the right language and interoperate between the languages, and then look for optimizations and other things like that. So just to give an idea, And once again, here we're saying basically project specific, but since compilers are really hard, if we actually tear apart that view that we can't ever peer down into a compiler, and we can actually put our science down into that level where the code is actually working at, we can actually build useful compilers. And I have some examples with integration, finite element, linear algebra in different places. So just to give an idea of what I'm talking about, take a simple integral. Perhaps this one here looking at cosine x times u of x, where u of x is some function that's evaluated, maybe a symmetry that comes from data, maybe something from some other calculation, and then some sign. So this is how a mathematician might write such a problem. But it'd be coded a lot faster if I just evaluated out that sign and gave a number, and then I would just have that evaluation of whatever data I had and some cosine. But even faster if I just wrote down numbers and evaluation points. But something's lost in this translation between these numbers multiplied by data evaluations and this mathematical presentation that was given and we understand. So how do we preserve that back and forth? One way is through a very simple language. So in this case, what I call int_gen, we define the fact that we're going to have u as some data, some discontinuous function, x is some symbol or in space, and we have a domain. And then I can just define this integral. And so it's not the prettiest little language you've ever seen, but it gets the job done. You can actually see what's going on, what the program is trying to do here. And then you can generate code, and it'll just generate to a file, for example. And so now I can use that piece of code in another place. I don't have to generate to a file. I could certainly generate to a shared object or something other dynamically JITted type object. So how does it work under the hood? It's actually pretty darn simple. I use SymPy to generate all these trees. Every ignition is pretty much all written in Python, just because I like to play around with Python and give people the ability to get down underneath. But you generate an expression tree from SymPy, and then I have BNF grammar, and you can just tear off pieces of this tree and go through and do what they call peephole optimization and start doing your domain optimizations there. So in that case, that sin x, I can see that there's no data. I can actually evaluate that on a domain. And this guy over here, I know I have quadrature points, and I can work around with that. So it's very simple, kind of structured. It turns out that, oh, and here's the code that it might produce, something like this, that looks a lot like those numbers and data evaluations. So it turns out doing other things like this is actually pretty simple, and tearing these things apart. So then we tried, I went and visited with Kyle and some people to do something for PyClaw, and so PyClaw talked already, so I won't dwell on it too much. But in PyClaw they have more or less these Riemann kernels that are solved every time step, and he has a Chilean earthquake that solved a tsunami, and so they want to make this guy as fast as possible to do more physics as they're doing it. And it turns out they have a pretty simple kind of time stepper or for these Riemann problems where they give a Riemann solver where they solve a Riemann problem, they do some flexible calculations and updating the cell. And it turns out most of the physics is in this Riemann problem. So if we're going to do that guy, we can change a lot of the code by just generating this Riemann problem in a fast way. And so based on the SymPy expressions, about 50 lines of code, we write, we have conserved quantities, fields, constant fields, and other types of constants, some sort of data that might come in. And I can write a shallow water. Kyle will have to help me if this isn't shallow water. So this is one of the contributed examples where we wrote up this little language, and they wrote up an example which means something to shallow water people or to people in fluid dynamics. And so I can just write a flux down that's all these conserved quantities. So Q is my conserved quantity. Rho, U, and E are more the fields you typically work with, or U is the velocity. So you can kind of see how now the people who work with PyClaw can just write this down and then generate the C code or some other code. And with that, we actually took, we're actually targeting faster code. What happens, so ClawPack was written in this older style of coding with Fortran. No worries about Fortran, but it was built for in a time when certain architectural architectural things were true that aren't true today, such as how the cache system works. And today, if you don't really use that cache system and stream through your L1 cache effectively, you're not going to get nearly as much speed. So we kind of rewrote the way they wrote Clawpack and Fortran, and it was slower in C++, but we changed it to a different method, of a cell-wise method, where we could just change how we actually iterate over this graph. And we had the same equation, we can actually just generate the different views. And we actually gained quite a bit of speed, and then Kyle to show off Fortran as well. I'll just go rewrite Fortran, and so he got the Fortran to be faster. But this is one of these kind of cases where you can kind of look at the machine change underneath. You really do need to change your operator in some different way. And so, kind of to a brief conclusion, we have lots of different languages we talk about, and in PDEs, there's a lot of ideas going back and forth about which method to use. How do I generate that method for a computer? How do I generate for any number of types of computers? And I didn't talk about it too much here, but we also generate for like the Intel mic clusters and CUDA and things like that. So you can really kind of hit not only a large number of architectures, but also a large number of equations very quickly. And we'd like to evolve this to be more where you just write down, like, I want some fluid solver here, and we can actually figure out even the better numerical method. And so in the future, you don't even have to know numerics, you just have to know that you have an equation, you want to solve some heat here, and you can actually do it on a supercomputer. So, and the thing I like to harp on is that back and forth software and mathematics abstractions really do matter back together. And since I came more from a CS and math background, it's always fun to get in and help geophysicists solve the same sorts of problems. So, thank you.
We've got time for questions. All right, well, I got one. I think that part of the reason things get designed the way they do, like in Clawpack, and probably to some extent PyClaw and Proteus for sure, is that when I came up through the system, I was taught object-oriented programming, and and so I'm wondering if you can help me make sense of this a little bit and think about a path forward, right? So what you're doing in object-oriented programming is you're taking a general, high-level language and you're adding to it, your class hierarchies and things, which they form a kind of domain-specific language. But when you do it the textbook way, you don't generally end up with your expressions that you can then operate on later. And so I think that's part of the piece that's missing, and it's attractive to me about moving towards DSLs at multiple levels of sort of the design. But I wondered if you could sort of point us in the direction of how to go about learning, I guess, how to really work with DSLs. And is that your objective with Ignition, or do you see it more as going and helping the domain expert come up with a DSL at their level, and then you'll be the one that figures out how to write the compiler for that, or the code generator for that domain-specific language? Yeah, so
I guess at the end of the day, compilers are kind of, here's the slide I was looking for. So compilers are actually pretty darn difficult if you want to take the entire compiler, right? You have to, even doing the Lexer, the parsers, the IR, optimizers, and code generation, all these sorts of pieces are like, there's multiple PhD theses written on each part of that. But the compiler guy usually only looks at the code, and he thinks in like sense of like some sort of machine code or something like that. And this is where the high-level goal of Ignition is more, well, a scientist actually has quite a bit of insight that they don't think about. Like, so if I write down that I have a conserved quantity, or that I have some physics I'm iterating over, they probably don't understand. They're probably not going to say to the computer, well, iterate this in a cell, do as much work in the cell before you move to the next cell versus doing everything for each row of your grid. And so there's some notion there that, you know, the domain expert, so finding this notation that can actually get the domain expert can say, here's all the stuff I'm doing here, and then letting the code generator not have to know about that sort of thing. Instead of making the scientist write at the code generation level, have them write at the science, like here's what I'm doing at this place, and here's how I'm doing that sort of thing. And then the view is like going from those two extremes, there's a lot of optimizations. And that optimization, for example, in Phoenix, one thing we do is we don't evaluate zeros, because when you have a higher order finite element basis, there's a lot of zeros that kind of come up. Now that seems a pretty stupid optimization, but there's a lot of places where scientific computing, you're actually doing quite a few zeros in your calculation just because you don't have to optimize that sort of thing out, or it takes so much time for you to write a native kind of guy to figure out where those zeros are or where I can cut certain things out. And so the view is that the domain-specific language, there's some experts that have some domain that they're going to be able to give you a better notation for, a better way of expressing. And then there's optimizations that sort of going to fit along many of these scientific domains, a lot of technical computing. And then there's the code generator is just the final best where the compiler writer, or you can go look at how they go to generate for one architecture versus another actually is able to participate. So in my view, there's not a good participation between the computer scientist, the mathematician, and the domain scientist. And I'm trying to help address some of those places and build tools around that stack.
I don't suppose you could talk a little bit about your code generation backend. Like, what methods are you using for code generation? Is it modular, and if so, how modular?
Yeah, it's not great right now. It's basically what is it? It's Mako with lots of strings, and so basically I use SymPy as my IR, and I know how to turn SymPy things into C code. So most of my manipulation happens on the SymPy level. I think yours is I don't know if yours is somewhat similar with Raffle, but I try not to go to do fancy code generation. I just generate C, and then I call a good C program, a good C compiler, because I think Intel has done a fabulous job at that, and NVIDIA's CUDA does a fabulous job at taking C code to PTX and things like that. So I try to stop at that point, but.
Well, okay, so what kind of retooling do you need to do when you want to target a different architecture? Is it just changing little things and tweaking little things and how the C code is generated?
Yeah, it basically, in this case, it was change how your iteration loop works. For my system right now, the more interesting things is what happens when we change physics or equations. But for example, pragmas are a big deal. Do I unroll or do I not unroll in this architecture? How big is my data on this particular, from one node to another node? How do I load balance across that sort of thing? It's not all built into Ignition at this point, but there's a lot more kind of top level things when you're building an application rather than the assembly code. So.
That's all the questions for now. Let's thank Andy again.